So how do we build circuits that can configure other circuits efficiently on the matrix? So remember, we have control over a neighboring cell's C and D inputs. So if we have one cell here and we have a neighbor, we can assert a 1 into this neighbor's C input, and we can send 1s and 0s on the D input and configure this cell's truth table and turn the cell into anything we want. So from any cell in the matrix, we have direct control over a neighbor of that cell. Well, theoretically, if we have control over this cell and we can configure it however we want, we can configure this cell so as to allow us to configure this cell. And how do we do that? Well, we configure this middle cell to say send a 1 into the C input and take whatever data value comes in from here and send that into the data input. And now this cell can send bits out of the D output, and those will go into the data input of this cell. And since this C input is set to 1, this is in C mode, the bits coming out of this cell's D east output will load the truth table of this cell. Well, if we can do that, we can configure this cell to do the following: to send a 1 into the C input of the cell to its east, and to take its data input and send that into the data input of the cell to its east. And now this source cell over here can send D bits out of its eastern D output and use that to configure the truth table of this cell. So theoretically, this is not too hard. We can use these intervening cells to configure cells more distant from the source cell and allow us to configure arbitrary cells within the matrix. That works great in theory, but there's a practical problem to it. So if we start with this source cell and we want to configure this target cell, that takes one operation. We put it in C mode, we send in the truth table, and after one programming cycle, we've configured this target cell. If we want to use this to configure this cell, we need to do two things. We need to first modify this so that it allows us to configure this cell, and then we need to actually use this to configure this cell. And then we probably need to reconfigure this cell to undo what we just did so that it's no longer configuring this cell. So this is actually going to take us 2 operations to get control over this. Now if it takes 2 operations to get control over this cell, and we want to configure this slightly more distant cell over here, well, we're going to need 2 operations to put us in a state where we can configure this cell. And then we're going to need 2 operations to reconfigure this to get it to stop configuring this. So it's going to take a total of 4 operations to configure this cell. And if we just extend this one more time, if we want to configure this as our target cell, it's going to take 4 operations to get control over this and set it up to put a 1 into this thing's C input and transfer D into the D. So that's 4 operations to do that. And then we'll go ahead and we'll actually configure this. And then we're going to have to undo this so that this stops asserting its C output to here. That's going to take another 4 steps. So this is going to take roughly 8 steps. So in general, this is order 2 to the n. We're doing towers of Hanoi basically. We're taking n steps forward, and then we actually perform our configuration, and then we have to sort of take n steps backwards. And if you've ever done towers of Hanoi, you know that for 8 disks it takes 256 steps, but the famous 64 disk version is a huge number of time steps. So 2 to the 64th, 16 billion operations, which means if we want to configure a cell that's 64 spots away from us, which is not that far, it's going to take us 16 billion operations to do that. That is really not a good day in the cell matrix lab. So we need a better approach to configuring cells other than doing this take 2 steps forward, 1 step back kind of approach that grows as order 2 to the n. So we're going to look at an embellishment on this basic idea of a wire called a multi-channel wire. So that's our next topic.